hello everyone. Welcome to another episode of the Koi podcast. Uh, so, in this podcast, as some of you have been following, we try to focus on conversations, specifically from early career researchers, trying to highlight different aspects of research and sort of bring in the stories behind the research and try to try to engage the young audiences on the varied nuances or the great research that a lot of our early career researchers are doing. Thus, Ashfaq Ahmed, he's a PhD candidate studying fluid and thermal science at Brown University. So today we're going to try and highlight uh, Ashfaq's recent paper that was published uh, in Remote Sensing of the Environment, which is one of the most highly reputed journals in the field of remote sensing. So just introducing you, Ashfaq, you want to tell a bit about yourself and the current research you're doing?
Yeah, sure. Thank you, Manojit, for this opportunity. This is, as you said, that I'm Ashfaq. I'm a fourth year PhD candidate. And right now I'm studying, well, more precisely, I'm studying the vulnerable Earth's component. The Earth is a dynamical system. It's kind of, it has kind of its own life, which was first proposed by Lynn Margulis back in her paper. It's called the Gaia hypothesis. It says that everything in Earth as if they interact with one another like a living organism. But not all of the component of Earth is as alive or as rugged as the other. Say estuaries or shallow water bodies of the Earth are one of the most vulnerable to any changes. Arctic Ocean, it's very vulnerable. Antarctic, these are vulnerable because um, you see, since the dawn of time, Earth were kind of stable until industrial revolution began, and things kind of started getting out of hand. Now, not all part of the Earth got their fair share, and estuaries are one of them. Question is, what is estuary? I will go in detail, but to sum up your question, Monojit, I study the vulnerable component of the Earth, and it so happened that most of them are water bodies. And my background is mechanical engineering, more precisely fluid mechanics. So from a fluid mechanics or geophysical fluid dynamics lens, I want to study those vulnerable components of the Earth.
Right. Yeah, thank you so much for that introduction. I really liked how you really set the context from a very earthly dimension. And it would be nice that throughout our podcast, we'll try to like zoom in a bit more into particular component. So first of all, I want to congratulate you with your recently published paper. The title of the paper is Estuarine Temperature Variability, integrating 4 decades of remote sensing observations and in situ sea surface measurements. And as I mentioned before, it has been published in Remote Sensing of Environment. It's one of the most reputable journals in the field of remote sensing. So kudos to you. Congratulations. I know as a fellow researcher how important a paper is to us. And so
Yeah.
you can also take this podcast as a sort of like a measure where we try to celebrate your paper.
I
So
was about
yeah,
to frame a photo in the wall, like your paper is public. When I got the email
right,
from the viewer, I was about to
right,
do.
exactly.
Perhaps someday I will
Yeah,
do that.
right, exactly. Because I know what a stressful process it is, and
Yeah,
feel free to like if you want to share some of your experiences with the review
definitely,
process as well.
definitely.
Uh, so yeah, so if you want to go a bit more into sort of the contents of your paper, because we really want our audience to sort of uh, understand the importance of your
Yeah,
work and
yeah.
why it's important. So
Absolutely,
yeah.
absolutely. Thank you, Manoj. This is something every researcher wants to share, but unfortunate thing is, as a researcher, especially from international universities, international lab and conference, we become so swamped up with our niche community, we tend to forget that our research has values to broader audience, regular audience as well. But to convey this message, it requires its own set of skill. Um, Many researcher can fluently, comfortably talk about all those fancy equations, all those fancy simulations and everything. But they tend to forget. It makes no sense to the general audience, right? Especially people who are trying to apply to the graduate program. Maybe they will be demotivated instead of being motivated.
Yeah.
So I know that when you first tell me you're going to arrange this podcast, I was thinking, how can I make a link between what I do versus how can I say it so that my mom and dad can understand?
Yeah,
So
exactly.
to this effort, I kind of prepared some slides. So let me actually share the slides with
Yeah,
you.
sure.
Uh,
Go ahead.
Tell me if you can see it, okay? Let
Okay.
me know if you can see it. Slideshow. You or to the audience, a series of pictures, and you need to guess what are these. So this is a satellite image from nighttime. This is Thames River and in London, and we have here Sumida River from Tokyo, and we have here what? Manojit, you tell me, what is this picture? This is River Nile.
Wait.
River
Yes,
Nile.
yes, exactly. Yes,
With
it
it.
was almost there.
Yeah. So one thing that is common, you see, since the dawn of civilization, estuaries has been the cradle of civilization. Why?
Right,
Because, oh, by the way, what is estuary? Estuary is where river meets the ocean. And estuaries are kind of the most productive land system on Earth. Every single meter square of estuary produce more organic material than the entire Earth
right,
combined. So it's a
right,
kind of crazy statistics. And this is no surprise that 22 big cities out of first 32 big cities
yeah,
are located near estuaries. Why
right,
not? Because you have access to fresh water, you have access to rich biodiversity,
right.
fisheries, blue economies, everything. So it is only understandable that there will be good amount of research done to preserve and conserve our estuary system.
Of course.
And as you can see from this figure, all lights, it's
Yeah,
lightened up.
exactly.
People live
Yeah,
here. Look at the surrounded stranded
absolutely.
area.
Yeah,
There's no river,
exactly.
no fresh water, no civilization.
Right. So I remember, and this is related to your work as well. Uh, there's a saying that the history of civilization is actually linked to the history of estuaries. So
Absolutely.
it's more
Think
from
about
a like
River Ganges.
from
Yeah,
yeah,
River
more from a
Ganges.
philosophical or
Yeah,
perspective, but I think also from a scientific perspective, I think what you're going to show is gonna be relevant as well.
yeah.
So
From a philosophical perspective, yeah. Think about a guy 50,000 years ago. Maybe he went to ocean and then came. He had to come back because it's salty water. It's deep. You cannot make a lot of things out of it with that time's existing technology. So they had to uh, gather together in estuary and kind of it promote the socialization of human as well from philosophical historical perspective. But from our perspective, yes, we have the rich biodiversity, we have the rich fisheries, blue economy, freshwater access, transportation, everything here. And not just that, you have another thing from a scientific perspective is, as I told you, that in estuary, river meets the ocean. Now, river has what? Fresh water, right? Sweet water.
yeah,
Ocean, on the other hand, has salty water. So it's
yeah,
a mixing region between fresh water and salty water, low density water versus high density water, low turbidity water versus high turbidity water. So a lot of different properties of water are mixing up here. Some
right,
crazy interesting fluid dynamics is happening. So this is a playground for all the enthusiastic fluid mechanics people who wants to study fluid mechanics, either from space, either from observation, either from laboratory, it doesn't matter. Estuaries are the place where you will get everything. You will get,
right.
these are the video, you will get cute little animal. You will get
Mhm.
birds. You will get like swamp of birds. You will get
Yeah,
cute ducks, fish. You will get happy people. So estuaries are the
right,
place where you have an arrangement and gathering of every good things in this world. Well, of
right, right.
biology,
Absolutely.
estuary, this is what I study. So I will
Yeah.
say all good things about estuary. You
Yeah.
stop me if I go out of hand.
Yeah, no, all good. Yeah.
Yeah, so this is why I one of the major part of my PhD is focusing on estuary until now. Of course, and then at the
Uh-huh.
future time I will be more focusing on Arctic Ocean, which is again
Yeah.
people say Arctic Ocean is the largest estuary of the world, but I'm not going to study Arctic Ocean from an estuary perspective. This is going to be a separate project, the second project of my
Right.
PhD. But as of now, let's keep our conversation focused to estuary. And
Right.
happy to take your next
Yeah.
question.
First of all, that's absolutely great. So first of all, thank you for that introduction. I think it makes very easy for us to understand the context, and I think you have done an absolute brilliant job to set the context. So do you want to tell us a bit more about the content of the paper that you recently published and what you try to focus on over there?
Definitely. That is stored in temperature, but it's a long name. I wanted to shorten the name, but it kind of my professor said that okay, it's okay to be detailed with your paper, so that
Right.
people
Yeah.
search anything. They search sea surface temperature, they find your paper. They search estuary,
Yeah.
they find your paper. They search
Yeah.
observation, find your paper. So all the
Yeah.
keywords here.
Okay.
Which kinds of sets up the purpose. So question is why would we care about this? Why would we care about estuary? Okay, understandably, there are something to care about estuary, but why sea surface temperature? There are mud in estuary, there are turbulence in estuary, there are marine biology in estuary, there are fisheries in estuary. Why specifically sea surface temperature? Well, there are a number of reasons for that. To begin with, we need to take a step back and ask ourselves what is remote sensing, because everything in this paper we have done has been done through remote sensing, right? So let me, sorry, I'm shuffling between slides and
Yeah.
slides.
No worries.
It's for a greater purpose. Let me
Mhm.
back to the slide again. So what is remote sensing? I think this is important for the audience to understand. We all have some shallow knowledge about remote sensing, but I want to give you some context that might be relevant to everyone. So remote sensing is study and sense the Earth from a remote place, from outside of the world. This is why we call remote control, because we're controlling the TV from a, not by pushing the button of TV. We're far away from the TV. This is exactly what remote sensing is. We're studying and sensing the Earth's changes from a remote position. Now, this is a uh, picture of Earth with many grid system, you're saying.
Yeah.
This is an ideal standard 1 degree global resolution. What do I mean by 1 degree? It means that every single grid you are saying, by the way, Manojit, can you see my mouse?
Yeah, I can. Yes.
Okay. So as you can see, I'm creating a shape, a rectangle around every grid. Now, this is a standard 1 degree global resolution model. I know these are fancy terms, but what I really mean here is they kind of creates a large 1 degree by 1 degree, which is 110 kilometer by 110 kilometer grid scale of Earth. And they give you information about that grid, that specific grid. Now, problem is, you see, let's choose a grid. Let's choose this grid. As you can see, this big grid. I can see Sahara Desert, and at the same time, I can see some forestry. Now, a standard 1 degree global resolution model will give you understanding of what is happening in that one grid with one data point. So they will say it has 20 degrees Celsius temperature. It is equivalent to saying, okay, today Bangladesh's temperature is 20 degrees Celsius.
Right.
It makes
Absolutely.
no realistic sense, because maybe Dhaka's temperature will be 38 degrees Celsius. Sylhet will have 15 degrees Celsius. So it doesn't give you any local information. It gives you a broad
Yeah,
mean.
it's a more of a regional perspective. Yeah.
Exactly.
Yeah.
So this is the fundamental limitation of studying anything with low resolution data set. But still, we do it because in many cases, we need to understand the climatological view. So large scale data set, large scale result is okay for us to predict some future tsunami, some future El Nino, La Nina, some future climatological pattern. It works good. But when you come to think about regional aspects, say you want to understand what's happening in Dhaka, not in India or subcontinent, what's exactly happening in Dhaka, or more precisely, what's happening in Dhanmondi or Bonani, then you need high resolution. Otherwise, what will happen if you use low resolution model? You're getting a blurred image, a very with high uncertainty.
Right.
But when you increase your satellite resolution, when you get more and more information, you know, okay, fine, these are houses, these are streets, these are trees. You receive more information.
Yeah.
And this is exactly what we took as the philosophy of this paper. We will study everything from a very high resolution model. Now, question is why? After all, this is a water body. We need to understand when there will be rain, when there will be storm. And for that, we really don't need high resolution. But still, what? Why? Then for that, to answer this question, let me share another slide from my actually PhD candidacy exam. I know that everything that I'm going to say will look, everything is all over the places, but I promise you I will connect all the dots. So
Yes.
let's just know that high resolution model has its own limitation. And this is why we tend to look at, low resolution model has its own limitations. This is why we tend to study things from high resolution model. So some of the changes in ocean happens in few meter scale. So whirlpool.
Right.
Now you can never see it from a global resolution model.
Right. Right.
Some of the estuarine processes happens within 100 kilometer. Low resolution model will never give you this information.
Yeah.
Some of the biological events, the jellyfish bloom, they happen in a kilometer range scale. So you need high resolution model, and so forth. Using low resolution model, you can predict global ocean circulation. You can predict, you can predict a lot of things. You can predict sea ice extent going high and low. You can predict that, but it doesn't solve the local policy, local problem.
Right.
So this is where I began my PhD. Say this is Narragansett Bay. Narragansett Bay or Narragansett Estuary. This is located in the junction between Atlantic Ocean and Rhode Island Sound. Those who doesn't know where is Rhode Island, many people don't. Rhode Island is very close to New York and Massachusetts. It's a state. It's one of the smallest state in US. But thankfully, Rhode Island has the largest estuary system in New England in the East Coast. So this is very important, not just for Rhode Island, for New York, for Massachusetts, for Connecticut, for all states. So this is why there are a lot of research, a lot of funding in studying this Narragansett Bay. To relate it with Bangladesh, Bangladesh also has Sundarban, right? Sundarban mangrove, which is one of the largest estuary. And not just Sundarban, all these southern jela, say Bhola, Feni, Chittagong, all the connection between some sort of river in that jela and Bay of Bengal. So estuary, Bangladesh is very rich with estuary systems. If you look at the map, all the southern jela, they are connected with river system and ocean system. So this study are highly relevant for any young generation student who will stay in Bangladesh and will contribute to Bangladesh economy, Bangladesh dynamics. Bangladesh is a brilliant playground for this.
So this kind of study has like a more applications in like a global context as well.
Absolutely. So for a second, forget about this is Narragansett Bay. Think this is Bhola in the south, and in the north, say this is Mymensingh.
So, there's some similarity actually.
So clearly in the north is exposed to less water body, and south there are a lot of water bodies here. So any local policy who wants to make a weather forecast in the southern district in Bhola, will he get data set from the southern area or from the northern area? Of course, southern area, because their region will influence their weather system.
Right.
Problem is, if you use low resolution data set, the entire picture becomes one single grid system. It will give you only one temperature point. And you cannot any place. You cannot storm, you cannot properly predict drought, you cannot properly predict agricultural important information, you cannot predict anything with limited information. And this is exactly why we used Landsat satellite. Landsat satellite out there since 1984. It has been there since ages, for last four decades. And it gives you information in 30 to 60 degree, 30 to 60 meter spatial resolution. Which means that instead of combining 100 by 100 meter square, it will only combine 30 by 30 meters square, which
Yeah.
is amazing, which is
Yeah.
great. You can retrieve a lot of information from that. So this is the one thing. And another thing is, I will come back to the question, why sea surface temperature? Now, sea
Mhm.
surface temperature is important from many angles.
Mhm.
First of all, I want to give you some fact. Let's stop sharing. Let's discuss
Mhm.
about surface temperature.
Yeah.
Um, I'm going to ask this question to you, Manojit.
Yeah, sure.
Tell me, how long is the atmospheric column? How long the atmosphere is spread?
You mean in terms of
Yeah, the atmosphere.
uh, okay, so I don't have the number off top of my head, but I want to say 5,000 kilometers
Oh,
or close or no?
it varies. When do you draw
Yeah,
the line of space? But
yeah, yeah, yeah,
5,000,
yeah.
maybe a little bit to stretch.
Yeah.
500.
It depends on which
Yeah,
stratosphere
exactly.
or
If
like
you go
which.
beyond 300 kilometer, you start seeing space, the dark,
Right,
empty space.
right. Exactly.
So all these, say, 300-meter sphere, all the temperature that the entire atmosphere absorbs, all the Earth's temperature. Tell me, how deep layer of ocean we need to absorb the similar temperature? So 500-meter
Mm,
atmospheric uh,
atmosphere.
absorption. What
Yeah.
is the equivalent depth of ocean that might absorb the same amount of temperature?
That's a really interesting question. I've never thought about it.
Mhm.
I expect that it has something to do with the well, the relative
Heat
heat
capacity, right? Heat
heat
capacity.
capacity. Yeah, yeah. But
So
I don't have that
500,
number.
500 kilometer length of atmosphere versus how much ocean depth? Give me a number.
Do you want me to guess? I'll take a educated guess. Um,
500 kilometer of atmospheric column.
yeah.
How much ocean column?
Mm, 100 meter, 100 kilometer.
100 kilometer. So five is
Mm,
to one.
yeah, something
Okay,
like that. No.
it's only 3 meter. 3 meter of
Ah,
depth contains or absorbs all the temperature that the entire atmosphere could absorb. 3 meter of.
right.
So
Yeah,
ocean is extremely sensitive to
yeah.
anything that we are doing to the earth.
Uh-huh.
And we
Yeah,
tend to say, because it's easier for us to say that, okay, plants, forest, trees absorbs all the heat, all the carbon
yeah,
dioxide. But in reality, ocean absorbs almost all the carbon dioxide.
yeah.
Ocean is the number one absorbing parameter of the Earth's carbon dioxide, carbon monoxide. It's not the tree.
Hmm.
The tree comes second.
Yeah.
So uh, the point is, after absorbing all of these things day by day, year by year, decades by decade, ocean's temperature is getting higher, right?
Higher.
Ocean's average temperature is now probably five folds compared to 100
Hmm.
before. So
Right.
problem is, as the ocean's temperature is increasing, it will have profound implication on oceans biodiversity, oceans
Yep.
dynamics, ocean circulation, oceans turbulence, ocean energy system, energy cascade, every single thing.
Hmm.
But for a layman, they won't
Hmm.
think about their relevance, right?
Yeah.
Even to their relevance, larva and plankton, they are
Hmm.
extremely sensitive to any sudden
Right.
changes in the ocean. If your fall or spring comes late or earlier,
Hmm.
plankton cannot bloom properly. The
Exactly.
larva dies. The
Right.
entire ecosystem collapses. So
Hmm.
that they do or we do, it will directly or indirectly impact uh,
Yeah.
phytoplankton, zooplankton.
Right.
And at the same time, problem with estuaries or water is shallow.
Hmm.
Unlike deeper 5 4 kilometer ocean,
Right.
estuary is very shallow system. So it
Yeah.
has thermal inertia, less thermal capacity. So
Right.
it can go high in temperature, low in temperature very fast compared to the ocean, which we have seen in our result that in Narragansett Bay, the estuarine water uh, increased way
Hmm.
faster, way more severely than its neighborhood Atlantic Ocean.
Right.
So
Right.
we'll kind of ruin the entire fishery system in the vicinity, in the locality. It will disrupt the blue economy. It will disrupt biodiversity. The birds. So by the way, birds cannot hatch, or their eggshell becomes extremely fragile when the temperature is high. Tortoise cannot breed, or their gender change with temperature. So you have many implications. So
implications.
Shellfish, say crabs, their shells becomes acid. So if your temperature is high, then the water contains more acids, so their shell becomes vulnerable. These are biological implication. At the same time, increasing water temperature kind of changes the pH of the soil. So it impacts your agriculture. It impacts your wheat, your grass, everything. So even from a layman's perspective, it's easy to understand if we keep increasing the temperature of the water, especially estuary, it will have concerning impact on our
And just to add like a follow-up question. I know that in this study you have done a time series analysis of the Landsat imagery. So in terms of like a very lame question is like, why do you think that monitoring like in a long span of time is important for like for in case of like, for example, the biodiversity you were talking about? Like how can this be used by practitioners, the time series that you have created?
That's a very good question. From a very, so I'm going to give you an example, might not be very relevant. Say you have the grade of a student, or the result sheet of a student when he was in grade 9 and 10. Now you have these two information. Now you cannot predict if he's a good student or bad student. But if you have his result sheet from his class 1 or grade 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can consistently this guy is doing good, or consistently this guy is doing bad. Similarly, we focused on Landsat because Landsat has last 40 years of data. Resolution data. So if we map all the data, in fact, I will show you what we see from the map. This was one of the important results from my paper. So this is an important result. In the x-axis, I'm showing the year from 1984 to 2022. In the y-axis, I'm showing the mean temperature. So we have subdivided the Narragansett Bay, the entire bay versus a part of the bay. This part is called Mount Hope Bay. So the black curve is Narragansett Bay. The red one is Mount Hope Bay. If you look at the black line, you will see it's increasing. The mean temperature is increasing. At the red, this is a very dangerous rate. We figured out that the rate of this increase in Narragansett Bay is 5 times larger than global ocean temperature range. This is not only for Narragansett Bay, all the estuaries in this world are their average temperature is increasing in an alarming rate, in a dramatic rate. It's only because, well, there are many reasons, but I will specifically highlight 2. Number 1, they're shallow water, right? So shallow body, they change the temperature faster. And second problem has something to do with the way we socialize, we make our industrial system. Since I began with estuaries are very productive. So it is by default that there will be a lot of industries, there will be a lot of economics, commerce near the estuaries. And when it happens, you throw a lot of industry dump to the estuary. And this causes eutrophication. Do you know what is eutrophication? Explain it to the audience, because
so eutrophication is when in particular like organic waste or is thrown into like a water body, then it over time it decomposes and some nutrients are available.
Exactly. Eutrophication, it's kind of nitrogen based waste. When you throw it in the water, they create a bloom of phytoplankton. And then this phytoplankton is become so thick that sunlight cannot penetrate and your animals die, simply speaking. So this is another way to ruin estuaries. So it's happening from both sides. The global average temperature is increasing, estuaries are dying. There are more industries are growing up, and they are throwing more waste, and estuaries are but they are dying from 2 ways. So this is important for us to focus on. And then I can show you one figure here. This is another important result. Let's forget
Mhm.
about the right side. Let's only look at the left panel.
Mhm.
So what I'm showing is in every single decade, so every 10 years, there are 40 years, the winter average temperature is increasing, spring's temperature is increasing, summer's temperature is extremely,
Mhm.
it's an extreme rate, and fall's temperature
Mhm.
is increasing. So summers are getting way warmer, winter
Mhm.
warmer. So this is a important result
I
from.
think what's very alarming from this figure that I've seen in your case is like even in global temperatures, sometimes the increase in temperature is thought to be a bit seasonal with more impact on the summer. But your results clearly show that this is not only summer trend. There's a significant change in other seasons as well. So yeah,
Exactly. We often tend to think, okay, yes, this summer has been the worst summer of last
yeah,
10 years. We only
yeah,
focus on summer, but it's not only
summer.
summer, throughout the year, throughout the
Yeah,
year. So this is an important
right.
take that this is
Yeah.
alarming. And then I can go on more, but I think what's important, it's the important footnote here that is Bangladesh is a very estuarine land. So all these
Mhm.
risks should be equally applicable to Bangladesh as well. Unfortunately, we cannot study Bangladesh in that depth because we don't have much in-situ observation.
Mhm.
There needs to be more on-site temperature measurement, salinity
Right.
measurement, turbidity measurement, which we lack. When
Mhm.
Fun thing, when I was working on that, I communicated with few of my junior friends
Mhm.
with, and I wanted to do the same
Yeah.
research on Bangladesh. But
Mhm.
unfortunately, there were almost no data in Sundarban area,
Mhm.
in Bhola area, in
Mhm.
no. So I was blank. Now
Mhm.
I still could do similar research from satellite data, but there are satellite bias. One of the
Yeah.
important things that I have done in this paper, I made a calibration between satellite data and in-situ buoy data so that I get
Mhm.
out of both board, but it was not
Yeah.
from Bangladesh
Yeah.
perspective. This is why I had to pause that part of the project. But
Yeah.
if anyone who is watching this, if anyone
Mhm.
can come to us with some sort of local data set that is there that I don't know, I'm happy to study that region with you
Right.
uh, from a both global satellite and in-situ perspective.
Right.
Happy to.
Yeah, I think that's a very because I know that a lot of some studies, like even for thesis purposes, they do collect some
Yeah,
aspects. One other aspect that I wanted to like ask you, and I'm not sure if this is an issue for your study. I know that especially in estuarine remote sensing cases, sedimentation becomes a major constraint where uh, part of the images might not have the best quality because of higher sedimentation. And I definitely, in my perspective, like past experiences trying to work in, especially the in deltas such as in Bangladesh,
mhm.
is that sedimentation and
Yes.
remote sensing, it sort of becomes a constraint. Did you find something similar in your study?
Yeah. So the funny because sedimentation and clouds are the two most challenging evil for any
Yeah,
guy who has remote sensing.
yeah.
Clouds are such a pain in the back because for clouds I had to skip tons of figure for the last 40 years because it was obliterated by cloud. Same goes to
Mhm.
sedimentation, but sedimentation is a rather easier way to deal with because we are really interested in the upper surface of the ocean, just the surface.
Mhm.
We're not going
Yeah,
deeper.
yeah.
So it was not much of a problem, but cloud was a serious.
Mhm.
But
Yeah.
we applied uh, machine learning method here to
Mhm.
eliminate cloud and to interpolate the cloud pixels with surrounding temperature. It is then in and of itself a research itself.
Yeah.
So in the paper, I did not highlight about that, but to interpolate or so first kick out the cloud pixel and then interpolate the cloud missing data with satellite
Yeah.
data, it was a on and on research.
Yeah.
But in this paper, we
Right.
didn't talk about it because this is kind of
Yeah.
off. Right? But probably I will write a
Right.
review paper on that.
Yeah, that's great. Yeah, so basically, thanks for mentioning that. Like, because a lot of our audiences work with remote sensing, and clouds are definitely one of the most talked about
Yeah,
factors. I'm currently working with, well, more in the Arctic, but I'm also trying to address this issue with clouds. So I guess it's a global phenomena and a global challenge for remote sensing.
Absolutely.
Okay, so basically, touching back, so basically, first of all, thank you for sharing such a broad perspective and also trying to break it down so that it's very easy for our audience to understand. Um, the other aspect, just changing gears now, is that uh, but a part of our audience, they're more interested in like becoming aspiring researchers, like trying to go into grad school, trying to understand what's there. So specifically in the dynamics, like if someone wants to study something like fluid dynamics or something similar, do you have any particular like recommendations for them?
I think so. There are two sorts of answer. One is, let's be realistic. Not all the time we have the luxury to select things that we love. In fact, in reality, most of the time, our life circumstances drives us to choose things that we choose. Now, probably 5 years before, or 6 years before, probably 10 years before, I might want to study electrical engineering or computer engineering. But it so happened that in my undergrad, I was selected to study mechanical engineering. And then
Mm.
I fall in love with fluid mechanics. And then at some point, I intentionally chose to study estuarine and geophysical fluid dynamics. But again, maybe for other people, if in every step, they will have to choose or select their subject or favorite topic based on the situation.
Yep.
And also, people need to understand who are applying for PhD. Unless you have a very clear and solid research proposal, you will have
Mhm.
to study what your professor wants you to study. So this
Yep.
this is another thing. But
That's the reality. Yeah.
that's the reality. That's the reality.
Yeah.
But I'm not saying it to demotivate you. I'm saying it
Mm.
to, uh, in fact, encourage you to have a great research proposal so that you and your professor can intimately work with that and contribute or do things that you love. And regardless, right now the world is so interdisciplinary. Even if your professor assigns you to do something, you can always integrate this thing with your passion, with your
Exactly.
interest. For that, you might need to study a lot. For that, you might need to brainstorm a lot. But you can definitely come up with a uh,
Right.
with an idea. So the world is so interdisciplinary. You can practically merge economics with 3D printing. There are
Yep.
ways to
Yep.
do that.
Yeah.
So if you love fluid mechanics, at the same time, you can study Arctic Ocean. At the same time, you can study the atmosphere of Europa or Ganymede. You can do that
Right.
because the
Mhm.
fundamentals are the same. The fundamentals
Yeah.
are Stokes equation, momentum and mass conservation equation.
Yeah.
So you know that you can do a lot of things, a lot of these
Mhm.
things. So I will say that opportunities are always there. Do not be frustrated or disappointed with the world's current scenario. It can be
Mhm.
political, be geopolitical, it can be regional, anything. Do,
Mhm.
do not don't let the situation demotivate you. If you have
Mhm.
the capability, if you have the courage, if you have the intention, research are needed. The way
Mhm.
the world is progressing, the way technologies
Yeah.
are progressing, we need researcher. There's
Right.
never uh, there's never a situation when the world will say we don't need any researcher anymore.
Yeah.
Like we need it
Exactly.
more. We need
You
it
know, I'll just add to that. You know, sometimes I get this question a lot from, especially from people who are not researchers, is like, can we be replaced by ChatGPT? Uh, I have my opinions on that, and I personally, like, this is my personal opinion. I think at some point, like specialized knowledge and PhD, at some point it will become more valuable. I know it's
yes.
not the most popular thing to say, but I
Mhm.
believe that at some point, the specialized knowledge that through a PhD, that not necessarily you need a PhD, but having any sort of specialized knowledge will become more valuable. What's your take on that? Like for like
I,
just
I,
to
I
address the
totally
elephant in the room.
I totally absolutely agree with you because see, the people who say that ChatGPT will take my job, I can guarantee you, 10 years ago, the same caliber people, they would be left out from job from other without by other people. The people who would be kicked out, they would be kicked out regardless of ChatGPT or Grok or other people. There historically there has been people, a community of people who were always kicked out because they were not good enough for their job. Now we can blindly or for our own comfort, we can blame everything to ChatGPT or AI. And this same community would blame more skillful people, or they will say that these people are more lucky, they have more family background, better family background. There are always people who used to blame.
Excuses. Yeah.
So the excuse and blame never works. I think uh, it should work, and
Yeah.
the level of work, uh, the level of expectation might be a little bit high in today's,
Yeah.
but at the same time you have more resource to upskill
Mm.
yourself. One funny incident, my buet professor, he completed his PhD probably back in 1976. He's
Mm-hmm.
very senior.
Mm-hmm.
So I saw his PhD paper. Uh, Now, what about it? It's plotting the contour of solar radiation. So contour plot, going to the place and manually plot the contour.
Mm-hmm.
We don't even think about it. We have so many software, MATLAB and Python, just
Mm-hmm.
plot contour in a
Yeah.
fraction of a second. But for him, it took him several months because he had to manually
Mm.
check all the data, then line a contour isothermal line.
Right.
He could explain that, oh, no, you guys are so blessed. You have this MATLAB. We don't have this MATLAB. No, no, no. These people don't
Yeah.
show excuse. They
Right.
do the work.
Mm.
So for
Mm.
us, we can do many things in a fraction of a second.
Yeah.
Same time, in future, it will be more easier. But
Yeah.
adaptability is the thing here. You need to understand
Yes,
the
exactly.
current state of the art, and you need
Yeah.
to level up your skill in a way that you remain top of the chain, top of the
Right.
biodiversity.
Yeah.
And it will, yes, it will take a lot of effort. It will take a lot of brainstorming and communication, sometimes networking. And one of the fundamental purpose that I think, Manojit, for your podcast is
Mm.
make people more aware of these things.
Yeah. Of
Because
course.
you are not interviewing me, you are telling me to share my research idea so that it can spread to broader audience, and
Yeah.
people can be directly benefited from a researcher instead of reading the book,
Right.
reading the paper by.
Exactly.
Yeah.
Absolutely. It's like for me, well, the type of books that's like absolutely I'll put my energy and read through are
Mhm.
basically autobiographies, like, learning about people, huh?
Yeah.
But if you think about it, like for us, like even like when I was starting my podcast, I could my research journey, I didn't really know the person behind the researcher, right?
Mhm.
And
Mhm.
it really struck me, like because sometimes I even read that person's paper, but meeting them in a conference is the first time I know who it is. And the whole philosophy behind this podcast is that can we sort of bridge that gap and sort of
Yes.
try
Yes.
to like bridge that gap and bring forth
Yeah.
the
If I
person
understood you,
behind the
if I
research and
understood you
also.
correctly, if I understood you correctly, you were saying that, okay, I'm reading a paper, but I want to understand the person who wrote this paper. How was he thinking? How did he think?
Exactly.
How did he get
Exactly.
this
Like for
development?
example, if you take our podcast today, you put into context so easily, like the philosophy that you had going into this research, right? And how
Mhm.
you took it, right? And how you explained it. I think that's very important, because not all the time we feel like, oh, that's just another paper, but it's not just another paper. There's a lot of effort, lot of thinking, lot of philosophy going behind like a particular effort. And the
Yeah.
whole like the whole point of this podcast is like to bring those forward. So yeah.
I,
uh,
I think
so
I think we
finishing right before we finish, sorry,
I
if you
think
want
you are
to finish.
doing a great job with that motivation in
Thanks.
this podcast.
Yeah,
Yeah.
and I always like to finish my podcast in a future driven note. So where do you see yourself in? I won't say 10 years because I know it's very hard to predict. But as a researcher, where do you see yourself in the next 3 to 5 years, or where do you see your
Uh,
research going?
that's a difficult question because the world is changing in such a dynamic way that sometimes we become confused. Is it progressing or declining? But of course, the mean result is it's progressing. It's always
Yeah,
progressing. It's not just like stock market, sometimes down,
yeah,
up, but
yeah,
overall it's going
yeah.
high. Uh, so for me, I want to see myself in. I don't know. It might be too much of stretch because people are watching, but I want myself to be one of the most important and influential researcher in the field of art. Art's a vulnerable component because there are people. who studies that, but I want to be one of those people who became uh, one of their kind. So here's the funny thing. If you have time, I can give you a little anecdote.
Yeah, sure. Go ahead.
So one of my favorite professors says that there are five level of researcher. Okay, number one, where we both are right now residing, you publish your paper. This is number
Mhm.
stage one. Stage two is you publish your paper and you started getting citations. A number of people
Mhm.
citing you. Stage three is um, people found one or two of your paper to be a must cite. So every time you cite, I don't know if I have one of your say, so Albert Einstein, if we use E
Mhm.
equals to mc square, we have to cite him,
Yeah.
or any kind of
Yeah.
distance or relativity thing. Stage five, stage four is you kind of become the legend of that field. Say
Everybody knows you.
Newton
Yeah.
or Albert Einstein or Paul Gauguin.
Sometimes in my field, I've seen people use the term God, like the God of
Yes,
science.
god of something. You become the legend, either living legend or dead legend, but you become the legend.
Yeah.
And
Yeah.
number
Yeah.
five is the topmost. This is way more than become the god or legend in that field, and that is people forget you, and they
Mm.
use their name as the method. Say Fourier. We,
Mm.
we use Fourier method all the time, but we don't
Yeah.
think it was a person. We think that okay,
Yeah.
this
Yeah.
is a divine thing that we need to apply to
Right.
break the signal.
Right.
We
Oh my
use
God. That was,
Laplace,
yeah.
but we never think Laplace was a person or Eulerian method. We never realized that Euler was a person, but we use their method. So you become the method.
I think that was the most insightful way to break it down. I've never thought about it like that. So kudos. I mean, kudos to your professor who put it like that. But yeah, that's absolutely like how we should think as researchers, I guess. Yeah.
Yes.
Yeah. But yeah, if you have anything else to add, or we can try to wrap up the podcast today.
I want
Yeah.
to add one last sentence, and that is if you guys want to collaborate, I'm always happy to collaborate in the research because I love to do research. I love to train people, which I have been doing since 2018 from my other company that I'm part of, Shabash Fakibaj. I always love to interact with students, engage with students, and share my knowledge, channel down my knowledge. And specifically, anyone who is watching it from Bangladesh or India or this area, if you guys have if you come to know that in your local vicinity, there are in-situ observations to study estuary or river from a closer perspective, come across to me, email me. I'm happy to study the same area with you, and we can together we might collaborate and publish papers and do research that might be important for the local community.
Absolutely, yeah. Thank you so much, Ashfaq Bhaiya. That was a pleasure to host you today. I think I considered this as a milestone for my podcast. So, yeah, but thank you for joining. And just wrapping up, I just want to touch base with my audience and just to summarize is that we saw today Ashfaq Bhai to really like try to put his research into a very personal context, everything from his global way of thinking and how estuaries are important to sort of break it down to the nitty-gritty of remote sensing. I think that speaks a lot about how we should approach research. It's not only that we go into and do the research, but it's also to think about it and try to put it into a greater context. And I think that makes it easier for us to researchers to wake up every day and to realize that what we are doing is actually important and not just another paper. So thank you everyone for listening, and please stay tuned with the Koi podcast, and don't forget to subscribe. So thanks.